Okay, so today we're going to introduce something new called concavity, and we're going to use the second derivative test. This can get a little confusing, so I'm going to try to go slow. The concavity stuff is pretty easy. The second derivative test gets a little confusing, but we'll deal with that when we get there. So you should be able to determine concave up and concave down. So we're working towards being able to draw really nice graphs based on some calculus work. Part of that is you need to know how to use concavity. We're also going to talk about points of inflection, define those, show you how to find them, and then we'll talk about the second derivative test, which will confuse most of you, but we'll work through it. It's a different way to find extrema of a function. So we already know how to find the extrema using the first derivative test. This is the second derivative test, which involves the second derivative. And then, of course, unfortunately, I cannot, but you should be able to roll your tongue. I cannot. Right. So you either can or you cannot. No, not roll your tongue like I can do a U. Like that. I can't do that.
Wait, you can? I can do it.
No, because I look stupid trying. Who else cannot?
Does this count?
Yeah, that works. Can't do that. Okay, concavity. We're going to deal with some fancy schmancy calculus definitions, and then I'll show you some pictures that will clarify what concavity is. There it is on the for the fancy definition. We've got an interval I, so it could be 0 to 2, 0 to 7, negative 10 to negative a million, whatever. It's concave up if f prime is increasing. It's concave down if f prime is decreasing. So the analogy that we had going from the function to the first derivative is the same as going from the first derivative to the second derivative. So we took the derivative, set it equal to 0. Wherever the derivative is positive, the function is increasing. Wherever the derivative is negative, the function is decreasing. Here, we do the same thing. We take the function f prime, we take the derivative of it, get f double prime. Wherever that f double prime is positive, it's increasing, and wherever it's negative, it's decreasing. We'll do a little bit more with that in a second, but that's the official definition. Not the most helpful thing in the world. That's why I'm going to skip it in 3, 2, 1. Here's more practical ideas. It's concave up if, I'll give you three things actually. It's concave up if it looks like a U. That's easy. It's concave up if it'll hold some water. So if I pour some water into the function, it'll hold some water in there. And it's concave up if all the tangent lines are below the graph. So three different things to explain the same thing.
All tangent lines
are below the graph. It's concave down if it looks like an upside down U. That's kind of dumb.
So like an N. Can you go back to the next one?
It won't really hold water, which makes no sense whatsoever. But we can talk about the tangent lines. If all the tangent lines are above the graph, it's concave down.
Could you explain that part with tangent lines?
Yeah, they're a little hard to see, but if you look at the 3 points there,
Okay.
those little blue lines are tangent lines, and the tangent lines are completely below the graph.
Oh, that's okay.
As opposed to this one,
Okay.
where it's concave down and all the tangent lines are above the graph.
Okay, that makes sense.
Okay. It's a veritable potpourri of sugar.
We decided to get like 2 of our, like he got 2 of his favorites, I got 2 of my favorites.
Are you the Schnickerdoodles and the Mariano's cookies? And you're the Chewy Chips Ahoy and whatever these things are?
Yeah.
Loft House?
Well, those are the best, but I can't eat any of
Loft House, delicious cookies. Look like this. She said with a German accent. Welcome to the Loft House. We got some cookies for you. Is that from something? Okay. So this is what I already said. So going back a couple slides, Here we talked about if f prime is increasing or f prime is decreasing. Now we deal with something a little bit more practical and say, well, if f double prime is greater than 0, it's concave up. And if f double prime is less than 0, it's concave down. We're going to use this more than we're going to use the other one. We're going to do the exact same thing we did with the first derivative, except now we're going to use the second derivative. So that means take the derivative, set it equal to 0, solve critical numbers, test regions, analyze that stuff, and we're done. Okay, ready? Let's start with that function. We want to determine where that function is concave up and concave down. What do you think we need to do first? Take the derivative, then what?
Take the derivative again.
Take the derivative again, aka take the second derivative. Then, once you get the second derivative, what are we going to do next?
Set it equal to 0.
Good, set it equal to 0. What will setting it equal to 0 do?
Find the critical numbers.
Good.
Put that on a number line. Called f double prime this time.
Yep.
And then test regions.
You should just teach. Take a nap or something.
Is it the same as the first derivative test?
It just tests for something different. The results that you get are different, but the method is the exact same. Okay, so it looks like this. I don't assume you had any problems taking the second derivative. Is that a safe assumption?
Yeah.
And you didn't have any problems finding the critical number? What is the critical number? Beautiful, we're all on the same page then. Okay, first derivative. I was feeling saucy, so I found the critical numbers of that. Completely irrelevant in this situation. Take the second derivative, negative 1/3. Beautiful. Okay, then, as John said, slap it on a number line. That number line is now labeled the second derivative number line, f double prime number line. That's why labeling the first derivative number line was so important, because now we're going to have a second derivative number line, and you have to be able to tell one from the other. It also helps when you have to plug numbers in. It reminds you where you need to plug the numbers into. So I graph negative 1/3. I pick a number over here. What's a good number over here to test? Negative 1. If I plug negative 1 into where? Second derivative. If I plug negative 1 in here, is it positive or negative? Negative, okay. Number over here? 0. Plug 0 into the second derivative, it becomes positive. Now, the only difference is on the first derivative, you drew plus and minuses below and then arrows above. Here, you just do CD and CU. Concave down, above the minuses. Concave up, above the pluses. Easy? Yes, sir.
There is.
You raise your hand to acknowledge Peter's question.
No, I have a question on this on his name.
You want to jump in on this too? Yeah.
So can this be used in replacement for the other one, or do we need to use the other one sometimes as well?
You need to use the other one also. The other one tells you where maxes and mins are. This just tells you concavity. And something else which we'll get to in a second.
Then for the answer, do we just leave it like that? Or do we have to?
Interval notation.
Okay.
Function is
So,
concave down from negative
from-
infinity to negative 1/3. Concave up from negative 1/3 to infinity. Okay, we good so far? All we did is test for concavity. Okay? Good. What? You don't want to share? She spit water at you? Oh. Let's skip this one. Just watch first, because it's the derivative is a little nasty. It's more of a practice on taking derivatives than it is on actually solving the problem. So I did all the work for you. We'll just talk about the final results. So ended up, okay, there's the first derivative. Then I took the second derivative to get that mess. You know, that's a little bit of quotient rule going on there. And then I cleaned it up, and surprisingly enough, it cleans up nicely to that thing. Okay. Now, what are the critical numbers for that second derivative? What makes it equal to 0?
It's 1.
And?
Negative.
-1, good. What makes a denominator equal to 0? Nothing. It's impossible. Because in order for that to be a 0 denominator, x squared would have to be equal to 3, which it never can, so beautiful. So I've got critical numbers of 1 and -1. Gesundheit. If I put those on a number line, I end up with something like this. Okay, the book likes to make charts. That's dumb. This is much more practical, and this is the one we're going to use, the number line method. Okay. So again, instead of getting bogged down in that derivative, we can skip ahead and just get to that thing. And again, that tells us where it's concave up and concave down, and your answers for those should be given in interval notation. Okay, any problems so far? If this were a first derivative number line, what could you tell me about -1? Forget about the CUs and CDs. If the pluses and minuses were still there, what could you tell me about -1?
The max.
It's a max because it's going from positive to negative. And +1 would be a min because it's going from negative to positive. So something special happens at the point 1 and -1. Now this is the second derivative. Something special has to happen at those points. Okay, they're not maxes and mins. They're actually something called a point of inflection. The point of inflection by definition is, well, there's a picture of them, but I'll come back to that in a second. There's the official definition. It's the point where concavity changes. It goes from concave up to concave down, or from concave down to concave up. You can copy this down, but it doesn't make any sense. Write down what makes sense to you. A point of inflection occurs when the function changes from concave up to concave down, or concave down to concave up. And it looks like this. Question?
Wait, how would they ask you for it? Like, in a question, what would they ask?
Determine the points of inflection of the following function.
And then you just take the second derivative.
Second derivative, critical numbers, put them on number line, test regions, changes CU to CD, point of inflection. Changes CD to CU, point of inflection.
Okay, so like if you had, you know, just like the -1 and 1, you would just say x point of inflections at x equals.
Yeah, the catch is point of inflections are usually given in point form, so you got to find the y value too. It's kind of a pain in the butt, but doable. Okay, so here we're going from concave up, and then all of a sudden it turns over to concave down. Here we're going from concave down and turns over to concave up. So you've seen those in a lot of places. They don't necessarily have to have a horizontal tangent line, as is illustrated over there. Got a lot of different things that apply to it. The last,
Never mind.
go ahead.
I was gonna ask, how come for the downward to upward is horizontal? I can't.
Just a fluke. Just happens to be the graph there. Doesn't have to be.
Okay.
Okay. This bottom thing, theorem 3.8, is the same thing we talked about with maxes and mins. That's the golden retriever thing. All points of inflections have to be critical numbers, but not all critical numbers in the second derivative have to be points of inflection. Yo.
So if it went from like a concave down to concave down, it wouldn't be a point.
Correct. It'd be some weird point that, why is it there? It could be an asymptote, could be a cusp, could be all kinds of different things, but it is not a point of inflection. Example of something like that would be, this is concave up, this is concave up. Strangeness might show up on a number line, but no point of inflection because it's not changing. Skylar, you got a question?
No, I fixed it by actually.
Beautiful. Okay. So find the points of inflection there. Notice two parts to that. Find the points of inflection and discuss the concavity. In the process of finding the points of inflection, you will automatically get the information you need for the concavity. John, I like how the hat has all the things I'm into, like high heel shoes, pink sunglasses,
Picked it
flip
up.
phones, CDs,
Green cedars.
green CDs. Yeah, and then what is this thing? This is oh, sales. This is the most demeaning hand I've ever seen. VIP shopper. Oh. And nail polish. This setback that causes women at least 20 years right here. Susan B. Anthony just rolled over in her grave seeing that happen. In fact, she might just rise from the grave and come and claim that hat, drag it back into the depths of hell with her. But don't feel bad about it, John. It's okay. You're over it.
Wait, so what do we do the same thing as concave?
Yeah.
And then what?
Second derivative,
Yeah.
set equal to 0. Solve. Number line. A second derivative number line. Test regions, concave up, concave down, concave down, concave up.
Oh.
Answer the question.
Oh, so this is like the other thing, it's like the same, just like more.
Okay. What do we got for critical numbers, kids?
0 and 0. 2. Oh, I did that too.
It's better than a lot of things. Could be reading
Scarlet Letter.
Scarlet Letter's not horrible.
I didn't think
Could be
that.
reading Tess of Dubervilles, whatever that is.
A brief history of physics.
That's a good one.
It's a light reading.
Grapes of Wrath, that's a great one.
I know that's terrible.
I hated that. I that and the Odyssey.
I love the Odyssey.
I love the Odyssey.
I didn't
like the Odyssey?
No, I
Yeah,
didn't
that was a
like it
good
either.
book.
I like reading those.
I really liked Light by Ellie Wiesel.
That was good.
That was good.
I like that.
Just used to.
Okay, so we are all in agreement that we have critical numbers at 0 and 2, yes?
Yeah.
Beautiful. Now what? Number line. Woohoo! Right. There is my number line. Okay. So what does that tell you about 0 and 2? They're points of inflection, correct. All we care about is that it changes. Unlike the first derivative test where you have to determine if it's a max or a min based on going positive to negative or negative positive, with points of inflection we just need to see a change. Over there I included the graph just so you can see what's happening here. That we have a point of inflection here at 0, a point of inflection at 2, and then it turns over. Eventually what we're going to be doing with the last part of tomorrow's lesson is taking this original function that we had and without using a calculator, that's the key, being able to get a really nice accurate graph like is shown here. You're going to be able to do this whole thing. You'll be able to find the min, you'll be able to find the points of inflection, and you'll be able to draw a pretty good graph of that curve. Yes?
So how would you like show, to ask you for the points of inflection, so how would you like work it out?
Just say the point of inflection occurs at 0, comma,
2.
and I don't know what the value is. So plug 0 into the original function to find it.
The original
And then-
function, not the.
Yeah.
The original, yeah, original. And then if you're talking about concavity, that should be given in interval notation.
Oh, so it'd be like 0, 0, and 2, negative 18.
Correct, thank you. Are they labeled there?
Yeah.
Yeah. Well done.
It's the original function, not the.
Correct, because you want to know the y value to find the point of inflection.
Or your constant points, are they protractors?
That one's a protractor, this one's a triangle. 45, 45, 90 triangle. But my shirt's trashed. I had a fight with the copy machine this morning. It didn't go well. I lost.
Yeah.
But it's like cop. That's what I
I fought the cops. No, not this morning.
Yeah, but yes.
Maybe. Yes?
So if they put an interval on like where that graph could begin, they had it at 2. Would that not be a point of inflection?
No.
Because now it's no longer changing.
Correct. Perfect.
Okay.
That's a common mistake. People have a tendency to consider mins and maxes points of inflection. Seldomly, if ever, are they points of inflection. In fact, they can't be. Because notice it's still concave up through this whole interval. It doesn't change until we get over here to 2. Here.
At points of inflection, you draw the tangent line on either side.
Either side of what?
The point, like, you don't know what it's about.
Theoretically, they have no thickness, so there'd be only one side. But yeah, if you think of it as a physical object having thickness, it would be the same thing. Okay? Are we good with this stuff? Pretty easy? Okay, good. Now things are going to get a little confusing, so I'm going to go slow, and hopefully this will make sense. The only thing the second derivative test does for you is what you've already done with the first derivative test. It confirms that a point is either a max or a min. So you're asking yourself, why would I do that if I could just stop with the first derivative? And to be honest, I don't have an answer for you. Most of the time, you're going to just use the first derivative test. So why would you ever use a second derivative test? There's 2 instances. One, when you have a function where taking the second derivative returns a nice, easy, pretty answer, like a constant. And number 2, more importantly, when you have a problem that says, verify maxes and mins or find the extrema using the second derivative test. In other words, it'll specifically say, use the second derivative test. It is a fairly common thing to see on the AP test, a free response question that gives you a function, asks you for the extrema using the first derivative test, and then part B will say, do the same thing using the second derivative test. So you do need to know it, but it's not the most practical thing in the world. It just changes one little concept. Let's suppose we have a maximum. Okay? What's special about that point? Tell me what happens at that point. It's a maximum. Good start. F prime changes from positive to negative. No, that is not a point of inflection. Because notice it's concave down over the entire interval. What does F prime equal at that point? 0. Good. So at this point, let's call it C. F prime of C is equal to 0. Okay, good. That's from what we learned with the first derivative. What can you tell me about the concavity? It's concave down. The way to say that is F double prime of C is less than 0. If you combine those 2 things together, it guarantees that it has to be a maximum. Okay, the first statement, F prime of C equals 0, tells you it's got to be a max or a min. The second statement using the second derivative tells you that it is a max because it's concave down. Now what about a minimum? What's special about that point? Other than the fact that it's a minimum. Beat you to it. Let's call that one, we'll call it G. Nah, not G. What letters don't get a lot of love?
Q.
K. K gets
Q.
more.
What's F prime of Q? 0. It's a critical number. It's either going to be a max or a min. What's the concavity? What's F double prime of Q? Greater than 0. Okay, that's the second derivative test. And I'll give you all the fancy schmancy stuff that goes along with it. Graph opens up with a critical number, has to be a min. Graph opens down with a critical number, has to be a max. Does that make sense? Good. Now let's do the calculus. Okay, so there's what we just said. F prime of C has to equal 0. That establishes that as a max or a min. And then if F double prime of C is greater than 0, it's a min. Okay, it's got to open up. And if F double prime of C is less than 0, it's got to be a max. It opens down. If F double prime of 0 equals 0, you're screwed. You can't use it. You got to go to the first derivative test. Okay, we're good with the theory here? Now I'll show you the practicality or how to apply it. And this is where things get a little bit weird because again, you'll continue to ask, why am I doing this when I can just do a first derivative test? Okay, can I go? All right. So we'll look at this one. All right. So I need to find the first derivative. That's easy. Negative 15x to the fourth plus 15x squared. Okay, so far? Find the critical numbers. So factor out a negative 15x squared. That'll give me x squared minus 1. So therefore, set it equal to 0. So my critical numbers are x equals 0 plus or minus 1. Okay, with me so far? Good. If I was going to, I don't even want to say that, never mind. Let's proceed with the second derivative test. So the second derivative test now, I think those three things could be maxes or mins. I need to use the second derivative to test. And all I care about the second derivative is the value of those points positive or negative? I don't care what the actual value is. So I need the second derivative. That would be negative 60x cubed plus 30x. You with me so far? Okay, now I need to know what is f double prime of negative 1. Is it positive or negative? So plug that in here. If I put a negative number in here, I get 60 minus 30 is positive, so that's greater than 0. So let's stop there. F prime of negative 1 is 0. That establishes that it's a critical number. F double prime of negative 1 is greater than 0. Is it a max or a min?
Min.
It's a min. Good. Okay, what about f double prime of 1? Put in 1, I get negative 60 plus 30 is negative. It's less than 0. What does that tell you? It's a max. And then lastly, f double prime of 0. 0. Question mark, question mark. We don't know. Can't use the second derivative for 0. Question?
So this is a replacement for like the f prime number line thing.
Correct.
So if it's like a critical number that makes it undefined, we don't use that?
Critical numbers come from where? What's when you say it makes it undefined? What do you?
Makes
F prime undefined you still use as a critical number. But a lot of times those end up being weird points and don't turn out to be maxes and mins like we'd like them to be. But you still have to respect them. Yeah.
When you're testing values, do you plug into regular f of x or prime?
Testing these values?
For like, yeah, like for the number line.
Plug into f double. You always plug into the function that's designated by the number line. So if I'm using a first derivative number line, I plug into the first derivative. If I'm doing a second derivative number line, I plug in second derivative. Okay, does this make sense? Yes or no?
Yeah.
Okay. Again, not the most practical thing in the world because more than likely you're going to stay with the first derivative because you can see if I was going back to the first derivative test, I'll do that in a different color so we don't get confused. I would simply do this. Test a bunch of regions, find out whether it's positive or negative, increasing, decreasing, and be done. But again, when you're forced to use the second derivative, you do this. Okay, it doesn't require a number line, by the way. You're just finding out values. Scott?
So why do we use those critical numbers into the second derivative?
Because these critical numbers tell me that these 3 points could be maxes and mins.
Alright.
Okay? Remember, the critical numbers from the second derivative tell me what? They could be what? But the points, let me ask my question again. What are the
Points of inflection.
thank you. They could be points of inflection. That's why we don't care about the critical numbers of the second derivative.
The numbers we plug in could be points of inflection.
The critical numbers of the second derivative could be points of inflection. Okay. Okay, does that help? Or does that help? Does that make sense? And again, realistically speaking, you're going to do this a gabillion times. You'll do this 4 times. Okay, unless it specifically says use the second derivative test. What do you got?
Don't you usually do the F double parenthesis for the number line?
If I was doing something else, yeah.
If you were doing this.
What we're going to do tomorrow then is we're going to take all this stuff we've done already, we're going to put it all together and be able to do a graph. So in other words, I'm going to take the first derivative, I'm going to find the critical numbers, I'm going to put them on a first derivative number line. I'm going to take the second derivative, put it on a, find the critical numbers, put it on a second derivative number line. Take all that stuff and start doing a graph. And there's some other things we need to do that you learned about in pre-calc, like x-intercepts, y-intercepts, asymptotes, that kind of stuff. But then put all that together and we'll eventually be able to do some graphs. And they'll be pretty accurate graphs, a lot more accurate than you could do last year in pre-calc, because we know some things that we didn't know last year. Okay, so skip through all this stuff, blah, 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 blah. Is there out there, okay? Yep, that's it. Okay, so there's the 2 sentences there for second derivative test. Stop. There we go, good. So sentences look a little bit different. These are the second derivative. And again, those 2 things. At the first derivative, it has to be equal to 0, and then the second derivative is either positive or negative, depending on whether you're getting a minimum or a maximum. Good? Okay, we're done. Yeah. Oh, so that's what it'll look like eventually when we put all that together. That looks a little confusing, but notice in this particular function, 0 is neither a max nor a min, but it does end up as a point of inflection. So something weird happens at 0 there. That's why something weird happens at 0. That's what that function looks like. So last year when you were doing graphing in pre-calc, I don't think you found the height of these points or couldn't even find those points. You just knew that it made like a curve. This year we'll be able to do all kinds of more detailed graphs and find the height of that, determine how quickly it climbs, how shallow it is, that kind of stuff. All right, we good? Day 43. So again, tomorrow we will go over homework from last night, go over tonight's homework, and talk a little bit about curve sketching. The lesson for curve sketching is not that long because a lot of it is a lot of review from last year. I also have the same handout or a similar handout to what you had last year to help you with that curve sketching. Okay, questions?